Thanks a lot, Carl. Thanks for having me. So yeah, this is joint work with my postdoc advisor, Graham Smith, and two of his students, Mohammed and Josh. And this work was done while I was still at Gilla. I'm actually now in between jobs, and I'll start a job, a postdoc at IQC and Perimeter Institute in December. And so our paper is about playing games with multiple access channels. Since I'm assuming that not everyone knows what a multiple access channel is, I want to give you like a very quick intro. So a multiple access channel is kind of the simplest network communication scenario, where you have two senders and one receiver. So a common example is that you picture a cell tower, and then you have two mobile phones who try to send their location to the cell tower. And the goal in the multiple access channel scenario is to, for each sender to transmit an individual message to the receiver who wants to decode both of them individually. Okay? In more mathematical terms, you have two random variables A and B, which are the input to the multiple access channel. And then the channel itself is just a conditional probability distribution, which gives you an output random variable Z. And you usually assume in the multiple access channel scenario that the two senders can agree on an encoding strategy before the transmission, but during the transmission, there's no communication between the two parties, okay? Which mathematically translates to the fact that the two random variables are independent. Okay, so we have this kind of no communication locality constraint between the two senders in this scenario. And the goal for the two senders is to transmit messages to the receiver through this joint channel that might jumble them up. And they both try to do this at a certain rate, which we call R1 and R2, and I will define this later in a bit more detail what I mean by rate here, okay? But just now for the intro, we call a rate pair R1, R2 achievable if the two senders can transmit information at those rates and the receiver is able to decode them such that the error goes to 0 in the asymptotic limit, okay? And since we have two rates, the corresponding capacity is a region in the 2D plane. And a typical capacity region looks a bit like this. So it's a convex area here. And it's composed of all the convex hull of all the achievable rate pairs R1, R2 that we can achieve in a transmission. And I will explain all of this in much more detail just now that you have an image in your head. Okay. And I told you before that in the communication scenario, you usually assume that the two senders are not allowed to communicate during the transmission, which imposes this kind of locality constraint in the whole communication setting. And this kind of links it up to quantum theory because as we know, quantum correlations are a strict superset of classical correlations. And this can be nicely formalized in the theory of non-local games. And we'll actually use that theory to address two questions that arise in this classical multiple access channel scenario. Okay? The first one is, if I give the two senders entanglement assistance, so I give them an entangled state and they can measure it and then use that to encode information, can you actually increase the capacity region? And the answer will be yes. And it's not just a simple yes, it's kind of complicated, and I will explain this in more detail. And then in the purely classical unassisted case, you can also ask how hard is it actually to determine the capacity region of if I give you a multiple access channel, how hard is it for you to come up with this curve, okay? And this was long kind of known and conjectured to be hard, but never really formalized how hard it is, and then we proved that using the non-local game theory that it's actually amply hard to compute this region. Okay? Yes? The second one is purely classical. Yeah. I will touch on that question. So bear with me. I'll explain what I mean by entanglement assistance. And I will also tell you, like, we don't have a full answer to the question that you're asking, and I'll tell you what kind of the question is there. Okay? So it will come up in a minute. Okay. So this is the outline for the talk. So I'll explain in more detail than in the beginning what actually the capacity region of a multiple access channel is and how we can use entanglement assistance to maybe boost it. Then I'll go through non-local games and give a very brief introduction because many people might already know about it. And then I'll show you how we can construct a multiple access channel in terms of a non-local game, and that will be the main object of study with which we can show our results. Okay? And the three main results are that first, entanglement can increase the capacity region of a multiple access channel. The second one, and this is a complicated part, is you might need unbounded entanglement to actually achieve the full boost in the capacity region. And the third is this classical result that to just determine the classical capacity region is empty hard. Okay, and then I'll conclude with some open questions. Okay, so in information theoretic terms, we need to define what does it mean to send information at a certain rate and what does it mean for an error to go down in the asymptotic limit. So this is the picture. The two senders prepared two code books, M1 and M2. And the size of the code book determines the rate of your code. And here the n is the number of times you can use the channel, and this will be what we take to infinity in an asymptotic limit. And once the two senders have agreed on two code books, in the encoding step, you encode the messages in the code book into the alphabet, into the input alphabet of the multiple access channel. Okay? So you get two sequences, AN and BN. And then the ith signal in each sequence you put into a multiple access channel. And we are here in the, we work in the IID scenario in which the channel for each signal is always the same and it always has the same statistics. And then using the channel n times gives us an output sequence Zn. And then the receiver receives this output string and tries to decode it back to the two messages that the two senders wanted to send. Okay? So he will come up with a guess M1 hat and M2 hat, which are the two random variables corresponding to the output, to the message of the channel. And we use an average error criterion, which is just the probability of this output pair not being equal to the message that the senders wanted to send. Okay? And as I said before, we call a rate pair or rate tuple R1, R2 achievable if the code books are of the according size. And we can make this decoding error go to 0 as we increase the number of times we use the channel. Okay? And the capacity region is then the closure of all achievable rates. And then it will lead to some convex area in the 2D plane, as I showed you before. Okay? All right. And so in information theory, you usually define capacity regions or capacity quantities in this operational way that you determine achievable rates, and then you take the closure of all of those. But then you also want to be able to compute this region. Okay? And this is usually called the coding theorem. And a coding theorem for the multiple access channel has been known for a long time, since the 70s. It was determined by Alsweder and Liao. And you can get it in the following way. You take two random variables A and B, which take values in the set A and B that are the input to the channel. And you consider product distributions on A and B. So A and B have to be independent, as I said before. And then you take some product distribution. And then the capacity region will be the convex hull of all rate pairs R1, R2, satisfying these three constraints here. Okay? So you have, so these are entropic constraints. This I quantity here is the conditional mutual information. And for the individual rates R1 and R2, you have the conditional information, conditional mutual information of A, the receiver, given that he knows B. And for the second rate, you have it the other way around. And then you have a constraint on the sum of the two rates, R1 plus R2, which should just be the mutual information between the senders kind of merged together and the receiver. So this, if you're familiar with Shannon theory and you know the classical channel capacity theorem, then this constraint here kind of resembles the capacity quantity. But the big difference is that you can only input product distributions between A and B. So this product constraint is a very powerful one and turns this whole thing into a non-convex optimization problem. Okay, so this kind of leads to the fact that it's going to be NP hard to actually compute this. Okay, but in information theoretic terms, if you don't care about how hard is it to actually compute this, this is a very nice formula because it's so-called single letter, which means that you don't need to take any limits when you compute a capacity region, and you only need to evaluate these entropic quantities on kind of one copy of the channel. Okay? If you're familiar with broadcast channels or quantum channels, then all of the capacity theorems for these channels are not single letter, which means that you need to take limits, and you can't even it might even be uncomputable somehow. Okay. Yes. Mm-hmm. Next slide. So right here. So yeah, very good question. So when you actually want to compute this capacity region, you want, okay, how does this look? You can kind of obtain it in the following way. You fix a particular product distribution on A and B, and then for a fixed distribution, the region that you get from these three constraints will always be a pentagon, because of these entropic inequalities that always hold. Okay. So if you fix some product distribution, you get one of these pentagons here. And then the round curve you get by varying over all product distributions and taking the convex hull of all these pentagons that you get. Okay? Yeah. So I don't want to dwell too long on this, but this is kind of the general picture. So for, it's kind of, you know, to get an idea of the capacity region of some arbitrary mag, it's kind of easy because all you do is you kind of, you draw product distributions, and then you evaluate this pentagon, which is just kind of obtained by evaluating these entropic quantities here. And then you do this a couple of times, and then you will get an idea for how the curve might look like. Okay. All right. And so as I told you, the nice thing about the Alswede-Liao region is that it's characterized by a single letter formula. So you don't need to take limits. You only need to evaluate entropic quantities. But the complicated part is this product constraint on the input random variables, okay? Which operationally comes from the fact that you don't allow the two senders to communicate during the transmission. So whatever they do has to be independent of each other. And now this kind of, this product constraint complication leads to two very natural questions. The first one is, can I use entanglement to overcome this independence constraint? And the second one is, since this is a non-convex optimization problem, how hard is it to actually compute this full region? Okay? And it was noted in a recent work by classical information theorists that the product constraint can actually be very easily turned into a rank 1 constraint optimization problem. And there's a lot of results and evidence that rank 1 constraints are hard to deal with optimization-wise. And so this already kind of hints at NP hardness of the whole problem, but it was never really formalized. And using the theory of non-local games, it's actually very kind of straightforward to do this. Okay, and this will be the last part of my talk. And so I told you before, non-local games are a very nice way to formalize somehow the difference between classical and quantum correlations. So we will use this theory, and we will actually in the capacity region focus on this last constraint on the sum of the two rates. Okay, so this is called the sum rate. So it's just taking the maximal value of the sum of the two rates, such where both of these rates are achievable. So they lie in the capacity region. Okay. All right. And I do have to tell you, because this is actually less straightforward than it might seem, how you can use entanglement between senders in a coding scenario. Okay? So we work in the usual tensor model where the two parties share some entangled state psi, and they're allowed to choose POVMs and measure their respective share of the entangled state. But to make this fully general somehow, what we want to do is we want to allow them to draw these POVMs. So for each, so what they do is they start with two random variables, A1 and B1, and for each value of A1 and B1, they have one POVM. And that gives them a certain conditional probability distribution on another alphabet A2, B2, which they can post-process using some functions to get like the actual input to the multiple access channel. Okay? And then the observation is that this blue box here is just kind of the measuring part and this post-processing, and this gives you a certain conditional probability distribution. And if you concatenate that with the actual MAC that you're interested in, the purple part here is just, again, a classical multiple access channel. Okay, but like somehow a component of the classical channel is the quantum correlation that you get from measuring an entangled state. Okay, but when we talk about entanglement assistance, what we actually talk about is the classical channel that's in the purple box, which takes classical input, A1, B1, and gives us a classical output Z, and then we talk about the capacity region of this thing. Okay? Yes. Yes. Exactly. So the entanglement allows me to overcome the independence constraint between A and B. So at the input to the actual MAC that you're interested in, but you still have the independence constraint here. Because you still want to, like the whole thing should fit into the classical MAC scenario. Okay, but we will see that this is enough to account for the boost. Yeah. So I hope everyone, this is a bit hard to formalize somehow, and I'm not 100% happy with the slide, so I hope this is kind of clear. And if not, please ask questions. Yeah, sure. Mhm. Like shared randomness. Yeah. Shared randomness is included in the original formula in a way. So this, like the capacity region of the multiple access channel allows for time sharing, which is basically shared randomness. This basically gives you the convex hull of all the achievable pentagons. So shared randomness is already incorporated into the classical coding theorem. And here you're really adding something more because you allow for correlations coming from entanglement. Yeah? So thanks for the question. Okay, I'll continue, and if you have more questions later, please don't hesitate to ask me. Okay, so we now know what it means to use entanglement for a multiple access channel. And now I want to talk a little bit about non-local games because we will use them to come up with interesting scenarios of where entanglement helps. Okay, so very briefly, and I'm not an expert on non-local games, but this is kind of the bare minimum that you need to understand the results. So in a non-local game, you have two parties, Alice and Bob, who are spatially separated, and then they receive questions from a referee and need to answer these questions in a way that they win the game. Okay. Winning the game, that depends on the game, so that's how you define the game. The most well-known non-local game is probably the CHSH game, where the two players receive a bit as a question, x1 and x2, and they need to answer with the bit y1 and y2, and then they win if the XOR of the answer bits is the AND of the input bits. Okay. More generally, you will have question sets x1 and x2 and answer sets y1 and y2, and then winning the game means that the question answer tuple is in some winning condition, which is a subset of these sets here. Okay. For experts on this, I don't consider promises, because you can turn every game with a promise into a promise-free game by just letting the players win on the questions outside the promise. So I will always talk about games where all the questions can be asked. Okay? If that doesn't tell you anything, don't worry about it. So this is kind of like the most general way to define this. It will change the winning probability. But I will talk about games that are promise-free a priori. If you have a promise, if you have a game with a promise, then you just declare a win for the players if they get asked a question that's not in the promise. The distribution of what? Well, it will affect your winning probability, and like the maximum winning probability, because it's easier for the players to win, right? Because they will win on like a couple of questions by default in a way. They don't have to answer anything. That doesn't matter. Well, it will matter kind of like when you enter numerics and when you actually compute the stuff that we derive. But for us, it doesn't matter because we only look at games that are promise-free by definition. Okay? Okay. And so now when you have a non-local game and you have the two players that are spatially separated, you now want to talk about the winning probabilities that you have. And you want to formalize somehow the available resources they have. And the first step, of course, is that the two players are classical. So when you only have classical strategies, what does that mean? Well, in a first step, you want to allow deterministic strategies, meaning that they both agree beforehand on some deterministic functions that, given the question x1, Alice will answer y1, and the function tells you which one, and the same for Bob. But then you also want to allow some of a shared randomness. So what you want to do is you want to have probabilistic strategies, which is just a convex mixture of deterministic strategies. Okay, so they also have access to some shared randomness, and then they can kind of just flip a coin and then use one of the deterministic strategies they agreed on. Okay, and the maximal winning probability omega g is defined as the maximum or all probabilistic strategies of winning the game. Okay, so kind of the probability of Alice and Bob winning the game if they have all probabilistic strategies at their disposal. And this winning probability depends on the distribution of questions that the referee uses to draw the questions. Okay. We will usually assume that this is a uniform distribution over the whole question set. Okay, and that's also how most results in non-local game theory are formulated. Okay. Now we want to consider quantum strategies. So very similar to before, a quantum strategy now for us is a shared entangled state and POVMs on Alice's and Bob's side that they can use to measure the entangled state. So we again work in the tensor product model. And the idea is that for each question, x1 and x2, Alice and Bob choose certain POVMs. And then measuring the POVM induces a probability distribution on the answers y I given xi. Okay, so I hope this line here is clear how I mean that. And we call omega star g the maximal winning probability using quantum strategies in this tensor product model. I will not talk about the commuting observable model. And this value here is sometimes also called the quantum value of the game, and the omega g is called the classical value. And coming back to the example of the CHSH game, it's not hard to show that the classical value of the CHSH game is 0.75. So that's the omega g. But there is a quantum strategy that achieves strictly more, namely 0.85. And so you have a separation between classical and quantum strategies. And this is kind of what I meant before by formalizing the difference between classical and quantum correlations. Is a question? Yeah. So CHSH is actually a promise game. So there you have a promise, and these numbers are actually when you have the promise, not when it's promise free. Because if you make this promise free, then the classical strategy goes up, with probability. But I think in the promise version, the distribution is uniform again on the questions. So that's what I meant before by saying that like these numbers always depend on the input distribution, on the distribution of the questions that you draw. Okay. But we will actually not be interested in the CHSH game because of the fact that the quantum value of the CHSH game is not 1. So even if you have quantum correlations, there's no way for you to always win a game. Okay? And we want to consider games where you do have a perfect quantum strategy. Okay? And one very nice example is the Magic Square game, which is a game where you have this kind of like 3x3 square, the tic-tac-toe thing. And the questions are for Alice, like Alice gets one particular row as a question. So for example, the second one here. Bob gets a column as a question, maybe the first one. And then they have to fill the boxes in the row and column with bits such that the following 3 conditions are satisfied. First, Alice's parity has to be even. Bob's parity has to be odd. And the row and column will overlap in one cell, and there they have to answer the same bit. Okay. So, for example, if they get asked the second row and the first column as the questions, then this filling would be a winning answer. Okay? Because the parity of Alice's row is 0, parity of Bob's column is 1, and they answer the same bit in the overlapping cell. Okay? All right. So now when you see like a filling like this, you can start trying to fill the whole square with kind of a deterministic strategy. And then you will quickly realize that with the last cell, there will be a problem. Because if you start filling them, and then this one is the last one, you will see that whatever I fill in here will violate one of the 2 parity constraints. Okay? This is actually, some people immediately realize that because when you have the constraint that Alice's parity in a row is even, there's 3 rows, so that means that the parity of all the cells has to be even, right, for Alice. And the same is true for Bob, only the parity has to be odd. So the cells can't both have odd and even parity at the same time, so there can't be like a perfect filling in a way, okay? And a filling corresponds to a deterministic strategy, what I said before, which is just like, they get some question and then they know what they will answer, which is kind of the filling. Yeah? And the fact that there's a problem in the last 9th cell means that the maximal winning probability using a deterministic strategy is 8/9. Okay? Because I can kind of handle 8 of the 9 cases by using a filling, but in the 9th one I will have a problem. And this is now important. If you now draw the questions uniformly, then you can show that the same value is actually also true for any probabilistic strategy. Okay? Because for uniformly drawn questions, for every probabilistic strategy, there is always a deterministic one which achieves the same value. Okay? Which I think doesn't hold if it's not uniform, but I'm not actually sure about this. But anyways, what Gilles Brazard et al. Proved is that for uniformly drawn questions, also probabilistically, 8/9 is the best that you can do classically. Okay, so the classical value of the magic square game is 8/9. And the cool thing is now, there is a perfect quantum strategy for this. Okay? So the strategy works as follows. You give Alice and Bob 2 EPR pairs, and they each hold 1 qubit of each pair. And then you fill the magic square with these observables, which are just the Pauli matrices, X, Y, Z, and I is the identity. Okay? And then to come up with a filling for the magic square, what they do is they just measure these observables on their respective share of the 2 EPR pairs. Okay? And the cool thing about this is that it's kind of easy to calculate that these choices for observables always produce the right parity constraints. Okay, so if Alice measures along the second row, for example, this will yield a string with even parity. Okay? And the same for Bob, just with odd parity along the columns. The nice thing is that observables commute along rows and columns, so it doesn't really matter in what order they do this. And obviously, since I just gave you one filling, it trivially somehow in the overlapping cell they do the same thing because they measure the same observable on two EPR pairs. Okay, so it's quite simple algebra to show that this is a perfect strategy that will always win the game for them, and so the quantum value of the magic square game is 1. Okay. Great. And so now those games will be somehow the main focus for us. Okay. Because we now want to define a multiple access channel in terms of a non-local game, so that we can use this separation between classical and quantum correlations. And the idea is that you just let the two senders play the game. Okay. And if they win the game, then the channel acts noiselessly on a certain input set, and otherwise it adds maximal randomness. Okay, so that's kind of the idea. In a bit more detail, what the channel takes as input the question-answer pairs for both senders. So Alice is the first sender, and her input to the channel is x1, y1. And for Bob, the input is x2, y2. And the channel is defined in such a way that if this tuple wins the game, so if this is in W, then the channel just outputs the question pair deterministically. Okay? But if it's not in the winning set, then you get a uniformly drawn question pair out of the channel. Okay? So this channel construction is inspired by a similar construction by Queck and Shore, but they considered so-called interference channel where you have two senders, two receivers. And using a multiple access channel was kind of like the main observation for us because it makes us, it enables us to prove these results that I will show you. Okay, so like in a bit more formal detail, so you have your non-local game with the question sets x1, x2, and the answer sets y1, y2. And you have this winning condition W. And on an input that is in the winning condition, you just get back x1 and x2. And if you're not in the winning condition, you get some random x1, x2, drawn uniformly from the whole set. And the operational connection to the actual game and the strategies in the game is that you can imagine the two senders first kind of asking themselves a question. So they choose some input distribution and draw x1 and x2. And then they use the game strategy to come up with y1 and y2. Yeah? So mathematically, this is kind of the distribution that you can generate in this way. And since we talk about max, you still want the first step to be independent. Okay, so you want kind of like they ask themselves the questions independently. And then the green part is the point where the game strategy comes in. And then depending on whether you use classical or quantum strategies, you can either get them by this kind of probabilistic strategy, which is just a convex mixture of deterministic strategies. Or you have the quantum strategies where this conditional distribution is obtained by measuring shared entangled state using some POVMs. Okay. But we can kind of already see here that the two things are very different as formalized by non-local games. And we now want to see how can we quantify that they are different. Okay. And this brings me to our first main result. If you have a non-local game, G, and you define the MAC in terms of the non-local game, as I showed you, then this constraint on the sum rate, this mutual information between just both senders together and the receiver, is a function of the losing probability of the game. Okay, this time the losing probability is actually defined in terms of an arbitrary distribution, because in the max setting, you do need to allow for any input distribution, not just uniform. Yeah? It has to be independent. And it's quite easy to show that this mutual information is just the entropy of the output random variable Z minus the losing probability times the kind of the maximal entropy you get when you draw the questions. Okay. And the observation now is that, let's say you want to maximize this right-hand side, which happens when the entropy term here is maximal. So the maximal entropy is in Z is just the question pair. The entropy will be log x1 plus log x2. So you want this to be maximal and this to be minimal, which means that the PL here is 0. Okay? So in a way, in order for the two centers to achieve the maximal sum rate, they need to draw the questions uniformly and then never lose. And this is impossible if you choose the right non-local game, as I showed you before. Okay? So if you take a game G that has a classical value bounded away from 1, they can't do both things at the same time. Okay? So either the winning probability is strictly greater than 0 if they kind of like draw the questions uniformly, or, as I showed you before in the magic square game, there's 9 possible question pairs, and there's one with a problem. So what they could do is they could say, okay, I just never ask that last question. But then they will never get the entropy of the output random variable to the maximal value. Okay, so there's kind of this trade-off. And so there's a way to kind of make this trade-off quantitative and say that if I have a non-local game where the classical value is strictly less than 1, then the sum rate is actually just bounded away from the maximal value. Okay? And we actually have a quantitative version of this. I just didn't write down the details to make it a bit more accessible. So this is for classical strategies. But if I now take a game where the quantum value is 1, then I can use the entanglement assistance in the way that I defined it before, together with this perfect quantum strategy that I know exists, to actually achieve the rate pair log x1, log x2. What I do is I just ask the questions uniformly, and then I use the perfect quantum strategy to always come up with the right answer. Okay? I don't care what answer, because like the channel only gives me back the question pair. Because like in these, for some non-local games, there might be more than one answer that does the right thing. And which one is kind of like determined by the P of the M outcome. Okay? But using the strategy, I will actually achieve a sum rate of log x1 plus log x2, which is the maximal sum rate I can achieve. Okay? So between the classical kind of no-go theorem and the quantum achievability theorem, I get the separation. The only problem is, in the way that we can prove it, the separation is not as big as we think it actually is. So when you evaluate these things for the magic square game that I showed you before, it actually looks a little bit bad at first. So the blue thing here is an approximation to the capacity region. I told you before that it's hard to compute this, but the magic square game is small enough that you can somehow trust your numerics, more or less. So this is obviously only an inner bound on the capacity region, but it's a good guess to the capacity region. Then the red line here is our bound on classical strategies, and then the black dot is this perfect sum rate point that I can achieve using the perfect quantum strategy. Okay. So if you zoom in a little bit, the separation that we get from the bound is 0.033. But the true separation, if you trust our capacity region, is actually 0.328. Okay, so there's like quite a big gap that we think is there. We just can't show it yet using our proof method. Okay, so this is one of the open questions I will mention later. Okay. So now that I've told you that entanglement increases the capacity region, we want to know how involved that might be. Okay. And there's a very interesting class of non-local games called linear system games that will enable us to show kind of the details of this entanglement boost. So for linear system games, you start with a system of linear equations over F2. So you have M equations in N variables. And then the game works as follows. The referee asks Alice one of the equations. So Alice gets a J ranging from 1 to N. And she answers with bit values for the variables appearing in that line. And Bob is asked one of the variables, so the I ranges from 1 to n, and he just asks with a bit value for that variable. Okay? And they win if either Bob's variable does not feature in Alice's line, or if it does, then they have to be consistent. So they need to answer the same bit for the variable that appears in Alice's line. Okay? And there's very interesting recent work by Will Slostra and Slostra and Wittig, where they exhibited an example of such a linear system game, such that you need entanglement to win the game, always, and you actually need an unbounded amount of entanglement for this. Okay? So they showed that the quantum value for this game is strictly bounded away from 1 for any finite-dimensional quantum strategy. And then they made this quantitative and showed that you actually need a maximal entangled state. And for the Schmidt rank D of that state, you have the following relations on the losing probability in terms of the Schmidt rank. Okay, so kind of the left part of that, the left inequality is basically saying this here. So if the D is finite, that means that the PL is bounded away from 0, and therefore the quantum value can't be 1. And the right-hand side is kind of an achievability result, meaning that if you allow for more and more entanglement, then you can actually make the probability go down, probability of losing. Okay, and so in the end, if you allow for infinite dimensional spaces and entanglement on those, you can achieve a quantum value of 1. So there is a perfect quantum strategy, but it needs unbounded dimension. And the main result here for us is that this separation that I showed you before between classical and quantum actually doesn't need classical and quantum. It just needs the separation between strategies in a way. So if you limit the two players to finite dimension entanglement, so that we know that the quantum value is bounded away from 1, we can turn this again into an upper bound on the sum rate that bounds it away from the maximal value. Okay? So if any D entangled, so entangled strategy using D-dimensional entanglement, for this particular mag defined in terms of this non-local game, has a sum rate strictly bounded away from the maximal value. And we again have a quantitative version of this. And on the other hand, if you can write down a strategy that as you take the D to infinity, as you allow for more and more entanglement between the centers, you actually approach this perfect sum rate in the limit D to infinity, okay? Which is kind of the corresponding result for what they showed using this quantum strategy. If you allow for more and more entanglement, you can actually get closer and closer to maximal winning probability of 1. And then another curious thing is that Will Slostra in his breakthrough paper showed that actually if you consider all the linear system games, so here I've been talking about a specific one that Wittig and Slostra found using fancy approximative representation theory. But if you just consider all the linear system games, then it's undecidable to determine whether the game can be won using a finite dimensional strategy. And so this now can be translated using our no-go theorem into the fact that it's undecidable to determine whether this point log m log n, so those are the two question sizes, can be achieved using finite dimensional strategies. Okay? I did put a star here because if you know about information theory and you paid attention before how I define entanglement assistance, I actually only considered a special case of entanglement assistance where they use the same entangled state for each channel use. Okay? And in theory, you don't have to do that. If you have if you use channel in parallel, you can have one big entangled state and then you use different amounts of entanglement for each channel. Okay? And it might be that using these more general strategies, you can actually achieve this and also decide whether you can achieve that. Okay, so this is something we left open because this is way more complicated to show than what we did. But using this particular achievable region using entanglement assistance in a way I wrote down before, we have these three results here. Okay. And then finally, I want to return to the unassisted case. So let's forget entanglement now. And we want to show that we want to kind of make precise why it is hard to compute the capacity region. And to this end, I assume that everybody knows about NP hardness and 3-set. So I want to, and you probably know way more than I do, but I just want to mention this non-local game version of 3-set, which was written down by Hallstatt, where you have n Boolean variables xi, and you have the clauses that appear in the 3-set problem. And then the game is actually very similar to the linear system game before. So Alice gets as a question one of the clauses and answers with an assignment for the 3 literals that appear in the clause. And Bob gets one of the variables and just answers with an assignment for the variable. Okay? And they win the game if either the variable doesn't appear in Alice's clause or if the answers are consistent. And then what Hallstatt proved is that using the PCP theorem, you can show that it's NP hard to decide for this game if the m, the number of clauses, scales linearly. That to decide whether that game has a perfect strategy or every strategy is bounded away from 1 is NP hard to decide. Okay? And so, again, using our no-go theorem, we can again turn this into a statement about the capacity region, okay? Because it's simple to see that this point here, the maximal sum rate point, can be achieved if and only if the corresponding game has a perfect strategy. And since it's NP hard to decide whether that happens, you can now phrase this in a way that it's NP hard to decide whether that point belongs to the capacity region or not. And you get this cubed scaling from using this bound for the classical value of the game. Okay? So if you contrast this with the normal point-to-point scenario, so point-to-point meaning you have one sender, one receiver, and you have Shannon's famous capacity theorem, there's actually there's an efficient algorithm to compute the capacity of such a point-to-point channel. It's given by the Blahoud-Arimoto algorithm. And if you want to approximate the capacity to precision 1 over n cubed, this algorithm gives you, does that for you in time n cubed log n. And if you believe that 3-set is hard, then our result tells you that to do the same thing for the capacity region of a Mac, this is exponential in n. So this formalizes this knowledge or folklore result that has been known for a long time, that because of this product constraint and the non-convexity of the problem, it's actually hard to compute this capacity region in general. Okay? And using this construction in terms of non-local games, it's actually very nice to prove this. All right, so I'll conclude. We talked about the multiple access channel communication scenario, which is in a way the simplest network communication scenario. You have 2 senders, 1 receiver. We know its capacity region. It's given by a single letter formula, but it's a non-convex problem, so kind of hard to determine. And using non-local game theory, we show that entanglement can actually boost the capacity of a capacity region. You might need lots of entanglement to get the full boost, to really achieve this perfect sum rate. And in general, it's undecidable whether you can do that. And in the unassisted case, we showed that it's NP hard to compute that, whether that point belongs to the region. And the open questions, some of them I already mentioned. So the first one, obviously, is if you see this plot, then you need to ask, okay, is the bound that we have optimal? And we think it's not. And I showed you that there's quite a big separation, or a big gap between the true separation and what we can show. So one thing is definitely to improve this sum rate bound. And this is actually just upper bounding the classical sum rate of a multiple access channel is a problem that classical people are very interested in, even if they don't worry about entanglement resistance. We showed this entanglement assistance boost using very specific multiple access channels that come from non-local games. So the question is obviously, does this work for any multiple access channel? And this is something I'm still thinking about. Then the next question is related to what we talked about before, that I only considered entanglement assistance in this very specific way, which gives you kind of like an achievable region, but then you want to ask information theoretically, what's the optimum that you can achieve using an arbitrary entanglement assistance, in the sense that if you use a channel multiple times, you don't want to restrict yourself to using the entangled state in the same way each time, right? And coming up with a formula and then maybe even proving that this is single letter, which we don't think it's true, but that might be awesome. That's a nice information theoretic open question. Another one is we only considered entanglement assistance between the senders because it's kind of this natural way for non-local games and for our channel construction. But obviously the most general thing would be tripartite entanglement shared between the two senders and the receiver. And there's some work on this in the quantum setting. So you consider quantum multiple access channels. But for purely classical channels, not too much is known here. And a purely classical question to conclude with this, because it's NP hard to compute a region, you cannot hope for you should not hope for an efficient algorithm to compute it. But it might still be nice and efficiently computable outer bounds for the capacity, especially for the sum rate. And this actually ties in with the first question, that we're very interested in better ways to upper bound the sum rate of a classical MAC. And since it's a non-convex problem, this is very hard. So yeah, with that, I'd like to conclude. Thanks. That might be true, but if you look at the point-to-point setting, so not multiple access, so you have one sender, one receiver, classical channel, then it's known that entanglement assistance doesn't do anything. It follows from the either the reverse Shannon theorem or the capacity theorem for entanglement assisted classical communication. Because basically, if the channel itself is classical, it destroys any correlation with the input, and then you can't boost the capacity doing this. For point-to-point. So there might be some interesting trade-off between the entanglement between the senders and the receiver. So I'm not saying this will be true here as well, but it might be a bit more involved than just using teleportation, because we know in the point-to-point setting that this doesn't work. I mean, this is kind of, I didn't actually say that. I should have said that probably. Kind of the cool thing about the entanglement boost here is that everything is classical. The channel is classical, the information is classical, but still the entanglement boosts the capacity, which is something that doesn't happen very often. If you have a purely classical information theoretic task, and then you add entanglement only in the encoding step, suddenly you get a boost, which is quite unusual somehow. So if you, let me go back to the slide with the entanglement assistance. So this is the way I kind of formalized entanglement assistance. So you have the actual channel, and then you allow this kind of processing box in a way, where the entanglement sits here. And then you treat the whole thing as a MAC again. Yeah? And if I now talk about the capacity region of this, then let me go to this slide here. In the coding task, you want to consider IID channels where each channel acts in the same way. Okay, so those are all the same. And if I replace this N here by the entanglement assisted box, this M channel, then that means that I will always use the entanglement. I use the same entanglement state in each step. And so whatever I get here will definitely be achievable by the coding theorem. But if I regularize, meaning that I take arbitrary entangled states and then I divide later by N, I might push the capacity region further out and then actually include this point that using only this scenario is undecidable. You know, it's undecidable whether this is included or not. But with the regularization, that might go away. And we don't know yet, because it's like one problem with regularized formulas is that you can't evaluate them. That's a whole problem we have with quantum capacity, for example. So even if we can prove a coding theorem for arbitrary entanglement systems, to actually determine whether that point is in there is still, you know, that might still be very hard. And for example, for the quantum capacity, there's very strange channels. It's completely different in a way, like information theoretically, but kind of like the nature is the same, where you, with this regularization, very weird things can happen where you need to take the N, kind of like the regularizing letter, in a way, the multi-letter thing. You need to take this to infinity to really see that the capacity is non-zero. So the regularization is a very weird thing. So it's as weird as undecidability in a way. I mean, I'm not saying this as a, you know, it's not in a formal way, but it's kind of, it's a very intricate thing. So it might just, like the whole effect might just go away if you have a full formula with arbitrary entanglement systems. So this is something we're still thinking about. So hopefully we'll be able to answer that. So we have thought about that, obviously. So especially this, I mentioned before that the product constraint can be turned into a rank 1 constraint. And then you could use SCP approximations to rank 1 constraints. But the problem here is that if you convexify the problem, the convex hull of product distributions is everything. So if you want to show a gap between what you can achieve with arbitrary distributions versus product distributions, then you will not be able to do this with convex problems, because they already, like, they will not show a separation. At least it seems like that is the case. Like we haven't thought about it for a long time, because this was kind of, we started really thinking about this afterwards when we wanted to talk about general max, where you don't have this non-local game bound. You still want to maybe show the separation, and then you want to handle the product constraint somehow. But just kind of like a, like we even tried simple things like these McCormick envelopes, which you have a bilinear constraint and you kind of replace it by linear constraints. And this just turns the problem into a convex problem, and then you kind of lose. So I guess with STP approximations, you might have a similar thing. But I don't know yet. But it's definitely something we're thinking about.